Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the Module 3 question from the CAPE Chemistry Unit 2, Paper 2 from June 2024. So this Module 3 question was a question about the industrial synthesis of ammonia, known as the Haber Bosch process, and it is depicted in the figure below. So here's the figure. We have species going in at A and B. Then we have E, we have F, we have D here, and then C is like a recycle or a feedback loop kind of thing. So we're being asked to identify the species represented by the labels A, B, C, and D in the figure below. So the question is asking us about the species that's represented. That's the keyword here. So the species, so we know that we are supposed to name some chemicals or some specific compounds, right? And so here we are, here's the answer there, right? At A, we're gonna have nitrogen coming in, and then at B, we're gonna have hydrogen coming in. So let me just put these on the diagram as I'm saying it. So we're gonna have nitrogen gas coming in up here. Then we have hydrogen gas coming in down here. And then at C, we have recycle. As I said, it's like a recycling that's going on there. So if the N2 and the H2 comes through and it's not used up in the reactor vessel, which is what E is. So let me just label that. That's the reactor vessel, right? That's where the reaction is going on between these two. So if it comes through F and not all of it was reacted, then it will be fed back. So in C, what do we have? That's unreacted N2 gas and hydrogen. So any of it that's unreacted will get fed back into the reactor vessel. And then in D now, what do we have? The ammonia would have been produced in here, right? In that reactor vessel. It comes through here, and then this is a expansion chamber. So let me just label that. That F is an expansion chamber. And so that's where the ammonia that was produced here and fed here, ammonia gas, would get condensed to liquid ammonia. So what would we be drawing off here at D? We will be drawing off that liquid ammonia. Okay? Liquid ammonia is what will be coming out at D. Okay? So that's what we have. So those are our species, the chemical species. Okay? All right. So let's go ahead now. All right. So part B says, use an equation with state symbols to indicate the process that occurs in vessel E in the figure above, right? So as we said earlier, let's kind of go back with that. Okay, yeah. So we have to use an equation so we know there's a reaction that's going on that we have to show. There's a reaction that's going on in the reactor vessel. And that is the reaction that we have to show, right? Using this equation and state symbols. So that reaction is actually how we produce ammonia. So here it is. We have nitrogen gas, right? 1 mole of nitrogen gas and 3 moles of hydrogen gas being equilibrated. So we use an equilibrium sign because it's an equilibrium process. And we get 2 moles of ammonia gas, okay? So that's what's going on in the reactor vessel. We are converting the nitrogen and the hydrogen into ammonia gas, okay? So that's what's happening here. All right, so let's go ahead now. Let's move ahead. All right, so it says use a chemical formula and state symbols to indicate the process that occurs in vessel F in the figure above. So as we said, vessel F is an expansion chamber. And in that expansion chamber, the gas, so let me just put it on here, the gas, right? The ammonia gas that would have been coming out of the reactor vessel, that gas is gonna get condensed to liquid ammonia. So that's how we're gonna get that liquid ammonia coming out in D, right? So what's going on in the expansion chamber? It is a condensation process. We're condensing the gas to a liquid. And so that's what we need to show here, okay? That's the process. So here it is. It's a condensation of gaseous ammonia to liquid ammonia. So we show NH3 gas going to NH3 liquid. Okay? All right. So let's move ahead now. Let's go ahead here. Okay, so now we're at 3-part D. And 3-part D says that the reaction to form ammonia product is favored towards the formation of product under certain reaction conditions. So there's specific reaction conditions that favor the production of ammonia. So we're being asked to state Le Chatelier's principle and use it to explain how increases in the pressure of the reactant support the formation of the ammonia product in the Haber Bosch process. So let's start by just jotting down. I'm just going to jot down here the equation for that conversion process. I'm just going to put back N2 gas with our 3 moles of hydrogen gas, and how that just kind of equilibrates to give you 2 moles of the ammonia gas. Okay, very important that we have our reaction up there so that we can see what we're gonna do with Le Chatelier's principle. Okay, so we have to state the principle and then explain how increases in the pressure of the reactants will support the formation of ammonia. Okay, so Le Chatelier's principle says that if one or more factors which affect an equilibrium are changed, the position of the equilibrium shifts in the direction which opposes the change. Okay, that's a statement of Le Chatelier's principle. So now we have to use this to explain, okay, how is it that if I increase the pressure of these guys, our reactants, how is that gonna favor the production of ammonia, right? And so if we think back to Le Chatelier's principle and how pressure, right, would cause a change in that equilibrium, we have to think about what pressure means and what pressure does. Like pressure means that you'll have a lot of the reactant molecules in a confined space. They're very close to each other, and so they'll bump into each other, and that will result in a lot more reactions and so on going on. But the key thing here is that, okay, if we've already established equilibrium and you're increasing the pressure of these, right, of these 2 gases, the equilibrium is going to shift in a way to kind of relieve some of that pressure. So, and the way that we generally come up with which side it's going to go on is we look over here and we say, okay, we have 1 and then 3, so that's 4 moles, right? We have 4 moles of gas on the left, and we have 2 moles of gas on the right. And so if I'm increasing the pressure of these guys, if I want to relieve that pressure, which is what Le Chatelier's principle says, if you're increasing the pressure, the equilibrium is going to move in such a way to relieve the pressure. The equilibrium is going to want to go to the side where there are fewer molecules, okay? So there are 4 moles total over here, and over here there are only 2 moles. So the equilibrium is going to shift towards this side, which is the product side. So it's going to shift towards the production of more ammonia. Okay? And so that's how by increasing the pressure of the reactants, we can favor the production of ammonia, because it will have to shift to the side where there are fewer moles. And so that way it can relieve the pressure that we put on the system. Okay? And so I just wrote that out here in words. It says that if the pressure of the reactant is increased, in order to relieve that high pressure, the equilibrium will shift to the product side where there are fewer molecules, as we just said here. Since there are fewer molecules on the ammonia side, this favors the production of ammonia. Okay? So because this is the side of the fewer molecules, this is the side where the equilibrium is going to shift, and voila, that increases the production of ammonia. Okay, so that's how increased pressure helps us in this particular process. All right, so let's clear this and go ahead now. So it says that this is the same statement here, that the reaction to form ammonia product is favored towards the formation of the product under certain conditions. And so they say we're supposed to now identify the unique feature of starting reactants that is most responsible for the exothermic nature of the reaction. So I have kept the equation here. I'm just going to erase these number of moles here and just keep the equation there, okay? So it says identify the unique feature of the starting reactants that is mostly responsible for the exothermic nature of the reaction. So it means that the Haber-Bosch process gives out heat. What would cause it to give out heat, aka be exothermic? So here's how we can rationalize that. We can explain that by saying that the large differences in electronegativity between nitrogen, the nitrogen atom, and the hydrogen atom makes it so that when they get together, right, they're going to form strong NH bonds when combined, right? And those are hydrogen bonds, as you might remember, and those are very strong bonds. And we're forming 6 of those. You see that? That we have 2 moles of ammonia being formed. And so in each mole, there are 3 NH bonds. So there are 6 total. And those are going to release a lot of heat. Remember, bond forming gives out heat. So if we're forming really strong ammonia bonds, NH bonds to make up ammonia, that's going to release a lot of heat. So again, the unique feature is the difference in electronegativity between the nitrogen and the hydrogen. That's what make the bonds that they do form when they come together very strong, which is exothermic. Okay, so now we have to state the reaction conditions that are specific to the Haber-Bosch process. And these are the 3 conditions that we often, come back to whenever we talk about the Haber-Bosch process. Is that we are going to use a pressure of 200 atmosphere, a temperature of 450 degrees Celsius, and then we're going to use a catalyst. It's finely divided iron or a mixture of iron and iron 3 oxide, okay? So these are the reaction conditions that are specific to the Haber-Bosch process. Okay, so let's move ahead now. All right, so this says that state how each component of the condition stated in D part 3 increases the rate of collisions of reactant molecules. So how is it that those 3 conditions that we just listed enable the nitrogen gas and the hydrogen gas to collide with each other rapidly? How do those 3 things facilitate that? So that's what this question is asking. So the first condition that we're going to look at is the pressure, right? And we spoke about pressure earlier. So here we're using a pressure of 200 atmosphere. That's very high pressure. And so what that means is that we're going to have a lot of nitrogen and hydrogen molecules being in close proximity with each other. They're going to be able to bump into each other very frequently. And so that's gonna be an increase in the rate of collisions of them because they're so close together, right? Due to that high pressure, right? And so that's how that translates to an increase in rate of collision. Now, the other condition was the temperature, and we said that we use a temperature of 450 degrees Celsius for the Haber-Bosch process. And so if we have high temperatures, what does that mean? That means that more nitrogen and hydrogen molecules, they have a lot of kinetic energy. So they're able to move and they can move rapidly, right? And so they're going to bump into each other with increased frequency, right? There's a lot of movement going on because the temperature is so high. And we know that that translates to increased kinetic energy. Okay? The third condition was the catalyst, right? So the catalyst is an interesting one to think about in terms of rate of collisions because the catalyst, right, what that does, so the finely divided iron or mixture of iron and iron oxide, what that will do is that it lowers the activation energy. That's what catalysts do. They lower activation energy. And so what that means is that when the reactant molecules do collide, they will have enough energy for the reaction to occur. So it means that the collisions that are taking place are gonna mean something. They're gonna eventually translate into the product being formed because you have a lower activation energy. So it doesn't directly affect the rate of collision per se, but it affects the rate of successful collisions, okay? Because when they do collide, they have sufficient energy for the reaction to occur. Okay, so this one is kind of an interesting one to think about in terms of rate of collisions. All right, so let's go ahead now. So part E says the Haber-Bosch process generates 2% of the world's carbon dioxide emissions and consumes 1% of the world's energy. Now we're being asked to indicate 2 ways in which carbon dioxide is emitted as a byproduct of the Haber-Bosch process. Okay? So here's what we have for this one. So we have a steam reforming process, right? We have a steam reforming process that's a part of this Haber-Bosch process, and that's used to produce hydrogen gas, right? That is how we produce hydrogen gas. It's through a steam reforming process. And so in that process, carbon dioxide is produced when natural gas is reacted with steam to form hydrogen gas. That's step 1 of that steam reforming process, right? And so the thing about carbon dioxide is that it can be readily oxidized to carbon dioxide. So that's one way that carbon dioxide gets, released as a byproduct in the Haber-Bosch process, okay? Now, step 2 of that steam reforming process is when we take carbon monoxide. So we take that carbon monoxide and then react that with steam. And that would produce carbon dioxide as a byproduct. And then, of course, we would get the hydrogen as well, which is what we're after, right? This is how we produce the hydrogen that gets fed in to that whole reactor vessel. So this is one way. This is a byproduct here, right, of that reaction where we have carbon monoxide reacting with steam. And then the step 1 was where we had the natural gas, so like a methane reacting with steam. And that process forms carbon monoxide gas and hydrogen. So in both of these steps in that steam reforming process, our objective is hydrogen gas, and we are getting that, but we're getting byproducts. In this case, the byproduct is carbon monoxide, but we know that that can get readily oxidized to carbon dioxide. So that contributes to it as well. And then now in step 2, we take whatever was left of the carbon monoxide, react that with steam, and that will give us more hydrogen, and then of course carbon dioxide as a byproduct. So these are the 2 ways, right, in which carbon dioxide is emitted as a byproduct of the Haber-Bosch process. Okay? All right, so let's clear this. Move ahead. So F. So F says state the effects of major limitations if the reaction in the Haber-Bosch process is done at STP. So what are the effects or the major limitations if the Haber-Bosch process is done at STP? So we have to know what STP is first of all. What's going on at STP? STP means that we're using a temperature of 0 degrees C and a pressure of 1 atmosphere, right? And you might remember earlier, right, the industry standard, what was done at industry is that we're using 450 degrees C and 200 atmosphere. So just look at how vastly different those 2 things are, right? This is what we do in industry. Industrially, that's what's happening. So they're saying, okay, if we don't do that, right, and we use a STP condition, so we have 0 degrees C and 1 atmosphere, how is that going to affect the process, okay? And so the first effect that we can think about is the effect of temperature. And we already said earlier how temperature comes into play to make the process effective, right? Why we use that temperature. We said that earlier. So if we're not using that and we're using 0 degrees C, what have we just done? What have we just done? We now are using too low of a temperature, right, at STP. So the reaction would take forever. The ammonia would take forever to get produced because the nitrogen and the hydrogen wouldn't be able to find each other. They don't have enough energy to move about, to collide and then form ammonia. So the reaction would take forever because it's too low of a temperature. 0 degrees C, no, they can't really move. They don't have any energy, okay? So that's not good. And then the second effect that would happen if we use STP with that 1 atmosphere, that's a very low pressure. That's too low of a pressure, right? And so if we're thinking about it from a Le Chatelier's principle standpoint, the equilibrium would shift to the reactant side. It would favor the side where there are more molecules. Remember that on the left-hand side, the reactant side, we had 4 moles, right? And so the reaction, the equilibrium would favor that side where there are more molecules so it can rise the pressure if we made pressure too low. Okay? So it would significantly reduce the yield of ammonia. We wouldn't get very much ammonia because the reaction would be stuck. The equilibrium would be stuck on the left-hand side, right? Where there's nitrogen and hydrogen. Okay? So that low pressure is no good for us. Low yield is what we would have. And then this one, it would take a really, really long time for such a low temperature. Okay? So let's go ahead now. So here we are at part G. Part G says identify 2 ways in which ammonia affects the environment. So 2 ways is that we can have eutrophication taking place, and we can also have smog being present in the air as a result of that ammonia. We can have soil acidification. We can affect human health in terms of the lungs being affected by ammonia. There are tons of ways that you could potentially list, but I just listed eutrophication, which is a big one, and then smog. Okay? All right. So let's go ahead to 3 part H. It says, as a fertilizer, ammonia is generally used in the form of an ammonium salt, right? State a reason for this, right? We're not going to use straight up ammonia is what this is saying. We're going to use it in a salt form. Why is that? The reason for that is that if it is used, if ammonia is used in its aqueous state, which is generally how it would be, right? If it's used in its aqueous state, ammonia would readily evaporate from the soil. So it would just vaporize and go away. And so it would not be very effective as a fertilizer if we just used it that way. And so now we're being asked to give the formula for any one of the most commonly used ammonium salts in fertilizers, right? Here, I've just given the formula of one of them, which is ammonium nitrate. But you could have given the formula for ammonium phosphate or ammonium sulfate as well, because those are used in fertilizers as well, okay? So with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right, you will see our Module 3 playlist, where you'll find tons more interesting content that will be helpful in getting you ready for this exam, okay? So thanks for watching, and we'll see you in the next video.